All right. Hello, everybody, and welcome to another webinar in our series about reinforcement learning in finance, from playing games to algorithmic trading. That's a subtitle, but today we are going a step further, or maybe we could say in another direction we go, meaning that today's topic is about the hatching of options in a Black-Scholes-Merton model, geometric Brownian motion, which we can easily simulate. We have seen already that we can use simulation to overcome the problem of too little data, of small data sets. And we are also entering another problem area in the sense of that so far we have basically worked with discrete actions, and only two actions were possible. So in the prediction game, it was about markets going up, markets going down, right? Pretty simple, 0, 1, or -1, +1, if we want to model this as a short long position game, right? But when we want to hedge an option, we need to control for the stock position and then derive the bond position in a manner that is not a discrete problem. We rather need to control a real valued number, and this requires a little bit of a different approach. So I want to quickly jump to the overview of the Q learning and to highlight the major differences that we would see in the code base that I'm going to present today. So let me walk through, maybe before I'm too fast, here you see the links, you have access to this slide deck. From the beginning, there you find all the links. I've checked, there are a few things obviously that don't really work on Colab with the newest notebooks. There are 2 new notebooks in the GitHub repository, right? Basically, you can load them with Google Colab, but I need to check. There's obviously one issue. I don't know, maybe with another version of TensorFlow or whatever it might be, right? So on my machine it runs, but on Colab there was one issue which needs to be figured out. Of course, you can join the Discord server of the group, of the community anytime, and you can also use this for chat, right? You can also use here the Q&A on GoToWebinar. I try to have a look on the 2 of them, so whenever you see me looking from my point of view to the left, right, then it's that I'm checking for the question. So these links should be all well known. You have access to them from the beginning. And now what I was saying, so let me jump over the wonderful success stories, but they're not the major focus of today. Reinforcement learning, the basic notion. So we have seen now many examples, and we have reinforced, I hope, our understanding of the single notions based on code that runs in front of us, right? Where we can really see over the single episodes how the agent learns and hopefully improves, right? We have an environment with which we interact, so we call this finance environment. So the finance environment was giving the agent exposure to data. In the beginning, pretty simple historical data. Then we simulated time series data. Then we added some noise to it. Also, I think a pretty interesting approach. And the agent is faced with a state. The agent can then take an action, right? And based on the action, the state of the environment is moved one step forward. So we go step by step. Even if you would imagine something like trading during trading hours, which is basically a continuous problem, we nevertheless would do this here in such an environment asynchronously. So we would step by step go forward and do not have any notion of time, in the sense of that we're not going to trade for 5 minutes continuously. We rather trade for maybe 500 single trades and or steps, right? So that's the difference. But this makes it nice that we can, for example, implement things much faster than in reality. Sometimes it's also good to do things slower than they are done in reality to get started learning, right? But usually with a machine, we would rather do it a little bit faster. Again, one step is simply the change from one state of the environment to another state of the environment. This could include something that's random or partially random. This is something that could be deterministic, right? When we think in terms of historical data, we simply have the data and move over the time series data set. So there's no randomness whatsoever included. We have randomness encountered in the form, again, of simulated paths, as well as in the form of added noise to the historical time series. That's the basic idea. Reward, target, two important topics and elements, notions here, right? Whatever the agent does, there is some reward or penalty. So we will work, for example, today primarily with penalties in the hedge context. So whenever there is a hedge error, there is a penalty in the form of the hedge error. We can do this, for example, in relative term, let's say in percentage values. We can do this in absolute terms, let's say in a currency, right? But the penalty is there, and in reality, this would be translated to a loss, right? When I make an error hedging an option, then I encounter a loss, right? And this is what we are going to make use of here as well. And the target is to minimize the loss over time. So, right, I mean, I want to minimize my hedge errors, and we would see visualizations where we see like the P&L over time for the hedging of an option, let's say over the course of 1 year, let's say 250 trading days, for example, right? So trading profit here might then be a hedging profit or a hedge loss, translated to the context of hedging options. So the policy, is what basically is to be learned. So the agent gets started with no prior knowledge of the whole thing, meaning the environment and the rules of the environment. It only sees the states and can learn from the changes from one state to the other, right? And then see what reward it is awarded or what penalty it must bear, right? And the policy itself is then usually represented by a neural network. That's our major tool. Doesn't have to be a neural network. There are other ways of doing this, but we are working primarily with neural networks, so that we then have something like deep reinforcement learning, deep Q learning, right? And the deep then refers to the deep neural network. So Q learning, and this is now something that I want to highlight, because when you think back to the implementations that we have seen, we have basically only two actions to choose from, or the agent. So there are two actions to choose from: market goes up or market goes down. And we have modeled this in a way that we have had the state parameters, let's say 4. So we can start with 4, and this was in line with the cardpool environment, right? 4 states, let's say, to keep it specific, and 2 actions. And there was like this connection being made, right? The relationship from a state is observed, an action is taken, and then there is the reward. Here we have the R function for the reward function, and R here obviously for the real line. Well, we can have something positive or negative here, right? When we speak of penalties, you would probably think rather in terms of some negative values instead of positive ones, right? And then the action policy is similar, pretty similar. We have again states combined with actions, and we get to a real value. So in the discrete examples, we had 2 labels, so to say, on the output layer, where we had real values for the 2 actions. Let's say action 1 or 0, right? 2 actions. The one has, for example, a value, current value according to the learn policy of 5, the other one of 2, and then we would choose when we implement the greedy policy, so the exploitation, then we would choose the one with higher reward, right? 5 higher than 2, so we go with the option that has 5. Now, with the control problem, we combine this a little bit differently. So we will see that we have, like in the features data, we have both the state values as well as the action, which means in our context is one action, namely the stop position that the agent chooses to hedge the option. And this combination is then assigned a real value. So it's just a single real value. So what we would have, let's say, for example, in a regression context, estimation. And still we have current reward plus the discounted future reward. But I wanted to highlight here the difference because the modeling approach will be slightly different. And given that we are dealing now with a real value, right, for our stock position, it wouldn't make sense to discretize this. Of course, there are some problems that could be cast, for example, let's say in steps of 0.1, right, from 0, 0.1, 0.2 up to 1, right? But here we want to have it rather as a the action really as a controlled quantity, which it is in practice, right? So representation is as before on neural network, no changes here with regard to the basic idea, because we know the neural network can learn not only, let's say, linear relationships, but also nonlinear relationships, which are important here. And the universal approximation theorem, this helps us here with approximating quantity or relationships that other approaches, let's say like ordinary squares regression, wouldn't be capable of doing so, right? But I think that's enough for review. Let's jump into the code, and you will see I have here at the beginning of the code, I have a little classifier. Is it here? Is it here? Where's my classifier? Work in progress. So this is actually something new that I've implemented. I was looking around, as everybody is doing, I guess, right, in books and in blog posts, whatever, but I didn't really find anything, any implementation. There are quite a few papers out there, but as usual in the research community, often this is the usual approach, right? They don't provide the code in detail. So what I'm now presenting, still work in progress. It works. So it's not only that it's kind of just rough. It works. It does the trick. But maybe when you now follow along and you see something or you have ideas how to improve it, I'm all ears, right? I'm pretty eager to learn how this can be improved. So a working version is presented, but probably there is still lots of room for improvement. Yeah, let's get started with the standard imports. Nothing special here. You might have noticed now we are in the 12th notebook. Basically, the beginning is the same, also with regard to TensorFlow Keras, which we use throughout. I have another notebook with the MAP regressor of scikit-learn, but everything else here is pretty much the same. So here I have commented out, for example, the random thing. So I want to get some randomness here included. So basically here, that's not really from this anymore. So Q-learning, the Dql agent, and I've said this, quite a difference in certain areas, but some things are pretty much the same. And what is pretty much the same here is the neural network. So I'm working here with, I think I might have added here a third hidden layer, right? I'm not using dropout. I go with the 24 hidden units, I think later on. So that's more or less the same, maybe one layer added, but overall, we stick to what has worked and has done the trick so far. With regard to the action space, now we have a linear activation, but we have only one action that we take, and this is real valued. So it's different to what we have had before. You might recall that we had like the argmax function a couple of times where we have chosen the option with a higher value. Here, we simply try to figure out later on, already here in the next one, right? We try to figure out what is the optimal action to be taken from an unlimited amount of actions that we have, given that we're dealing with a real value. So having spoken of that, we see here an opt action method. This is something that we haven't had before. I said we used argmax to choose the one with the highest value attached to it. Right here, what I'm doing, and this might be better understandable once we have seen the environment, and therefore I don't want to go into the details now. I want to first show you the environment. Then what is happening here is more easy to understand in this context. So down there, you might notice there's not that much of a difference. So I have called this hedge environment, but it's basically also like the finance environment, but since we are now dealing with hedging, right? So I still call it here finance, but I want to highlight that we are now using this for our hedge problem, right? So what are we dealing with here? So I said we work in the Black-Scholes-Merton model, geometric Brownian motion. We have in principle 5 parameters. The first symbol is just to give it a name, right? It has some name, or we have some imagination of what we want to simulate. Then we have an initial starting value. We have a strike price for the option. We have a maturity date for the option. We have here a short rate, and we have volatility. So here you see underscores, and this shall indicate that we are dealing here with maybe multiple different R's, sigmas, K's, right? So that we can simulate, let's say, for out of the money, in the money, at the money options for interest rate of 0, 1%, 5%, and maybe low volatility, middle volatility, and high volatility. So we allow here for different values for these 3 parameters. What I'm not changing here is the maturity date. So I keep this simply fixed, do a timestamp out of that, and the rest is stored. So steps is the number of steps that we use. I will work with 1 year. So this can of course be made flexible, right, open, but I work with 1 year, and the parameter that I can choose here is the number of steps. So if we go, let's say, pretty rough with 12 months or 52 weeks or 250 trading days, so this is what we can choose here. I think the rest, yeah, here we have an instance attribute which is called portfolios, right, which is a data frame, and we store there portfolios that we create during the hedging procedure. So we simulate the data. We have had the mean reverting process, the Ornstein-Uhlenbeck process previously when we used it for simulation. Now we go with the standard geometric Brownian motion according to the papers by Black-Scholes-Merton, right? Nothing special here. We use an Euler discretization, which is exact, which means it converges when we increase the number of steps here in this context. And as I pointed out before, we can have here multiple strikes, multiple short rates, multiple volatility values, and we choose them randomly so that the agent is exposed to different processes with regard to the moneyness, with regard to the short rate, with regard to the volatility. So high, low volatility, right, in the money, out of the money, that the agent has a bit more exposure as compared to simply a fixed strike, a fixed short rate, and fixed volatility. Here, once this is simulated, we put this here into a data frame, right? And then we can later on get the data accordingly out of the instance attribute here, data frame. Now with regard to the state, where I said, well, before we get into the details of the Dql agent, would probably make sense to have a look at the environment. And the question is, how do we model now the state of the environment, right? And we have here a couple of parameters. The first is the stock price itself, probably an important quantity, right? The second is the time to maturity, which I change, right? Of course, when we move forward in time, right, then we have a shortened time to maturity. Probably also important for the hedging. Then we expose it to the value, to the call value. So it's all about calls. I don't know if I've emphasized, this is all about calls here. Of course, the same exercise could be implemented with puts as well. But here the focus lies on calls. And that's basically it. So it's not more the call value, time to maturity, and the stock price. And when we now see here what it returns, you see that 2 additional elements are added. The first is the stock position itself, so meaning what the agent has chosen to be the hedge position, the delta basically of the option, right? And the second is the bond. The bond is then derived, the bond position is derived from the call value and the stock, because this is then what is quote unquote left over, right? So we can calculate this, but I have included this into the state, and this has improved the results tremendously. So I could have added other things as well. So we could discuss this. I haven't done like too intensive testing in this regard. For example, a strike is something that is usually known. So this wouldn't be too revealing, so to say, right? It's public information. When you want to hedge an option, usually you know what the strike is, for example, right? Short rate could be added volatility. I wouldn't say, or it can be argued, not really, right? So, but time to maturity, strike price, short rate could be something that we might include, but here I stick to, I think, the most simple setup. So stock price, time to maturity, and the call price itself. And then the problem of the agent is to come up with a delta, a hedge position, right, from which then the bond position is derived, so that the error, the future error, the hedge error is minimized. That's the problem. Let me have a look here. There's, I think, nothing really special with regard to the reset, apart from resetting bond and stock to 0, right? We don't have any position in this context. And when we now get started with stepping forward, and the agent now is supposed to take an action like plus 0.2, plus 7.5, plus 7.778, right? So a real value between 0 and 1 is to be chosen for the hedging, right? Like the delta, the values that delta for call is taking from 0 to 1. And if we get started at the very beginning, self bar is 0, right? Here bar after the reset, so to say, we give a reward of 0, nothing has happened. We move the bar 1 up, so 1, 2, 3, 4, right? Then the stock is set here in the form of the action. The bond is derived from the call value minus the stock position times the stock price. And then we get a new state. So this is simply the very first step. So no reward whatsoever. The agent chooses a position. That's the task of the agent, and then we adjust quantities accordingly. Then from the second step onwards, it's getting a bit more interesting. So we move the bar 1 up again, get the new state, so that we have the previous state and now the new state, right? And the portfolio now is as follows. We have the hedge position times the stock price plus the bond position. This can of course be negative, right? Bond position can be negative in this context, times, and here I include the short rate. If the short rate is 0, this longer term here isn't relevant, right? But if it's non-zero, then the bond might yield the short rate here. Of course, scaled by the time step dt, self dt that we have. So the P&L then is the value of the hedge portfolio minus the value of the option. Can be positive if the portfolio pays off more than the option is worth, right? Or can be negative if the portfolio value is below. And then we collect here all the information, the episode, the stock position, the bond position, the portfolio, the new state, the value of the option. Here I go with V, this could be called C for the call, right? V is more general for value. Then we have the P&L in dollar and the P&L in percent. The stock price, the strike price, R, and sequence. So that we have basically all the information per episode. Every single step is collected here in this data frame. We can later on use this and visualize results, etc. And then this is appended here to the portfolio. So this was recently deprecated or will be deprecated in the future, the append operation. So this should be concat, but with my pandas version, it doesn't complain obviously anymore. Now we come to an interesting question, the reward design. So you see I have played around with a few things. So one natural thing I think is to work with the absolute profit or loss, right? So I want to both penalize the derivation in terms of a profit as well as of a loss, right? It's not that we have here in the hedge context that we say, like in algo trading, oh, profit is always good. So we want to be exact here. Basically, it would be perfect if the portfolio is always exactly the same as the value of the call option, right? This is what we would like to have. Therefore, I go with the absolute difference and then put a minus sign here in absolute terms in front of it. If you would go with the absolute difference in this context. Then I've tried here the percentage values, so with a multiplier of 100. And here I now go with the percent value, so that we are dealing with relatively small numbers, so digits in this context. And we take the minimum of one in this value here in this context, right? Portfolio over the value -1, so that we get the net difference here. Again, take the absolute value and then the minimum between these two quantities. The stock position is then set to the action. So this is updated, if you like. Bond is derived again from the value of the option and stock position chosen. So after that, we should be good to go. Final check here, whether we have reached the end of our data set. So if we are at the end, done true, otherwise we go forward. So here there is no rule whatsoever that we would stop before the end of the data set. So we simply hatch the European call option from start to finish over the 250 steps or whatever we chose. It's roughly a 1 year time frame, a little bit longer for the majority of the option. Once the end is reached, we simply stop and say done, and then we can check what was the P&L, etc. pp. So with this background, I think it's now a little bit easier to understand what the agent is doing, right? Should maybe have a look here again. So the state, the features for the deep neural network are ST, stock price, time to maturity, call value, stock position, and bond. Right. So this is basically our action. The stock is the action that I choose. It's the hedge position. Given the current stock price, given the time to maturity, given the call option price that I observe. The bond is derived then from the stock position itself. So with that background knowledge, when we now have a look at the Dql agent, which in the beginning is not too different to what we've had before. I said maybe I've added here a third layer, but the structure overall is the same. And now the opt action method here might make a bit more sense, maybe, right? We have the replay down here, we have the act method here, and the opt action now does the following. It does an optimization given our neural network, the policy that we have approximated by the neural network. So we get something, oh, if you hear somebody, a dog barking, it's my little dog in the background. Sorry for that. And what I do here as an approach is, sorry, let me close the door. What I'm doing here, a little bit of a bark break. What I'm doing here is that I define a function f, which has as input the state. Recall what the state is. Current stock price. It is the time to maturity, TTM, and it's the call value plus the two positions, the stock position plus the bond position. And here it is the action that is to be optimized. So that's the basic idea. And how do we go about this? We have in the state and the array object, right? We have at the index position 3, we have the action itself, which is the stock, right? It's the delta hedging position. And we put A in here and derive the bond position accordingly. And then we predict, given the updated state with our neural network, we predict the expected reward, right? So with regards to the modeling here, what we do is exactly that. So we have state, 3 elements, and then we have the action, the delta position, right? And we have now an approximation for Q in the form of the neural network, right? And we simply change now A, right? This is done like here, for example, but we change now A in this context in order to derive the action which gives us the maximum expected reward. So this is what the optimization is doing based on this function. So the action that is to be chosen is derived by minimizing minus f state A, right? This is just the starting value, so that we, given our neural network, can derive here the optimal value. Here it is represented as A, but is later on the action. So A stands for action, right? And this is then translated into self.stock, right? The stock position, which is the delta hash position. So that's the optimal action. And you see, this is now a continuous optimization problem, not a discrete one where we just choose like action 0, action 1. Now here we must come up with a value between 0 and 1. And that's the function that does the trick. The act method is slightly different in this regard. That if it's not doing exploration, right, random actions, if it's not doing that, it calls opt action, exactly what we have discussed here. In the replay part, we also use the opt action, right, so that we leverage this here for the second time, in the sense of that we have the optimization here for the next state. So this is what I highlighted here. We have here, namely the optimization of the action in the next step. And for this little element, we also use the opt action method, so that we can come up with the optimal A here in this context, given the current version, the current state of the neural network, which represents our optimal policy. Of course, this is updated as we go. And speaking of updating, this is what is done here during the replay, right? Yeah, step by step, right? We know this is kind of what makes it slow, and that we update here incrementally one experience after the other, right? So we have a batch of maybe 32 that we take, and then we iterate here over the 32 experiences, historical experiences in the memory, right? And this is what makes it so slow. With other approaches where we are not using this algorithm, we would, for example, have like 1,000, 10,000, or even 1,000,000 data points and would train the model at the same time on all these data points. But here it is done incremental, right? Yeah, the reward is here accordingly derived, and we update the model as I was pointing out before here, step by step. But again, the optimization here, opt action, is what is an important step here in this whole adjusted algorithm. With regard to the learn method, I don't know if there is some difference whatsoever. I'm collecting here averages still as before, right? But they do not play really a role anymore with what I'm going to present later on. If you're interested, of course, you can still visualize that or inspect it, right? But I want to focus rather on single cases, meaning that we want to have a look at specific runs of the agent when it is hatching a call option. The test here again leverages the opt action method, meaning that we are not relying in any form on exploration when we do the test. Testing is done here always based on the then current optimal policy in this context. Yeah, I think that's basically it now with the changes. So control problem, instead of just choosing from a discrete number of possible actions, actually two, pretty simple case before, right? And we want now to implement the training here as follows. So I simply call this stock. If you fancy, you can call it, I don't know, German DAX or FTSE or Dow Jones Industrial Average or whatever. I get started, and this has proven to be useful with normalized values. So meaning I have a starting price for the stock of 1. I have K here set to 0.9, 0.95, 1, 1.05, and 10. So like 10% of the money 10% in the money. These are the maximum and minimum values here, right? The time to maturity is 10th day in January 2023. We are going to simulate this over 2022, so for 1 year. And you see here, I'm going with 365 steps. And as is usual, what you also see with other numerical methods, when you implement Monte Carlo simulation and do like a numerical hatching scheme, the more points in time you use for the discretization, the better usually the results are. The more rough you get, the higher the variability of the P&L with regard to the hatching. Sigma volatility is chosen 10%, 15, and 20. And if you recall, these three values, strike, R, sigma, are chosen randomly, so that when we do enough episodes, so to say, we will probably have the every single possible combination, and the agent has had diverse experience with regard to different constellations. So that's the basic idea. The agent itself, gamma is set to 0.95. Could also decrease that because it's not really making a difference. So as with the other finance environments, the agent, contrary to game context, cannot really change what's happening afterwards, right? So in a games context, of course, let's say chess, depending on your current move, you might have benefits or disadvantages in later moves. But here, although we have this random element, there is still no direct impact on the data given the action chosen by the agent. Right? The learning rate is set pretty low. This is proven to be better than, for example, with a 0-digit less. Of course, I need to define my agent. Otherwise, this is the agent. The longer the cells are, the more easy it is to get over them. So 50, and it is running. And what do we see now? We see throughout here negative values, right? And this is what I was saying before. These are penalties, and the best value is the one that comes closest to 0, right? So you see in between a total reward of -40, -41. Average currently is shown -50, right? This is, of course, in the beginning, highly volatile because we still have a lot of exploration. So there's simply random positions chosen for the hedging. And if I choose a position randomly, then I would expect, of course, higher differences, higher P&L values in absolute terms, right? Just in the meantime, okay, just checking. No, I think no open questions so far. Oh, there might be something in the chat. Okay, no, this looks good. So in the meantime, this is running here, and you see my comment with regards to doing all this sequentially. And in particular here now, we have this this optimization problem, this continuous optimization problem that we have, and this slows down things considerably, right? This is a relatively expensive approach and technique that we chose. The optimization that we had in the discrete context was simply the argmax, which has just to be implemented based on 2 possible actions. So this is a pretty fast operation. But now what is eating up lots of compute is the, when I recall here, the opt action, right? This can here, doing, I don't know, let's say 200, 500 iterations for every single optimization it implements. So that's quite a bit of difference, of course, than choosing argmax A or B, right? That's quite a bit of a difference for sure. So let's see how far this has come. This is through now 2 minutes, 4 seconds, and still epsilon, as you can see, is at 77. So meaning that 3 out of 4 actions are still chosen randomly. Let's do a test and see how it does in terms of the hedging. Let me go with the last one here. With the last one. So this takes a bit, again, it's relying exclusively now on the optimization. Before we had 3 out of 4 random actions are also pretty fast for sure. And we see now this is -25, -35, and -8. So what does this mean actually? Yeah, here you see that I go with the percent differences, right, in absolute terms. Meaning, like, for example, a derivation of +1 and -1% is translated here in -1. And then we add the rewards up over time. So again, the closer we get to 0, the better it is. So here we have a total reward, meaning total penalty of -9 percentage points. Right here you see obviously much worse, -35 is the absolute accumulated difference. So when we now have a look at the visualization here, first the data and then the visualization. I have a couple of visualizations. You see that for this particular case, episode 53, so we had 50 original episodes for the learning and 3 for the testing. So this is now all added into the single data frame. And in this particular case, S towards the end, it's the tail here towards the end, is pretty close to 0. B is derived from the value phi, it's the portfolio value. You see portfolio value and bond position are basically the same because S is almost 0, right? With regard to the value of the option, see here, yeah, the values are not too different, but we see differences, right? And the P&L here in dollars is like 0.0038, 0.0033. So not too large the differences, but still there are differences, and this is what we would expect. And with regard to the penalties, here we are most interested in the percentage values, and I've checked this, of course, back and forth. With regard to percent, the Keras neural network works better, much better, basically, and then with the absolute values. But I don't know, I cannot explain it at this stage. When I work with the MLP regressor, this works better with the absolute values. So I need to check, because there's one issue, quote unquote. So with the way this all works, I haven't figured out really a good way to normalize the data. We all know that data normalization, Gaussian normalization, whatever you want to use there, Gaussian or set score normalization is what you typically would use, gives much better results with the neural networks. This is given the way data is generated and the type of data that we are dealing with, I wasn't really able to come up with a good solution in this regard. And I think a couple of the issues that are still in there are related to this topic. And you see in percentage values like -3% and +2.2%. This, I guess, speaks a different language than just like the 0.00 something, right? Here we see the ST, the current stock price, and this was a simulation for K 0.9, for R 5%, and sigma 15%. So let's have a look at the graphics. I've spoken more about the graphics that I've shown. And we see here 3 things and 2 y-axes. So the red one here is on the right, that's the stock price. And for the call, you see, yeah, basically this is more or less moving in tandem, of course, on a different level. And you see the dashed line, which is the call value, the value of the option. Again, this could be done with a put option as well, but we do it with a call here, and phi is the portfolio value. So the way I'm plotting it here, it looks that the replication portfolio phi is not that bad compared to the option value, right? And when I now show the cumulative P&L over time, we see that, yeah, it gets started out pretty okay, then it accumulates losses here, it gets back into positive territory, and then towards the end it has a negative value, meaning a loss overall accumulated. This is now not like the reward, right, where we work with absolute values. This is now working with the P&L. And ideally, in an ideal world, when hedging works perfectly, then we would have here a flat line, right? This would be something that we would try to accomplish. So on the next slide, not slide, graphic, we see the P&L histogram in dollar terms as well as in percentage term. And you see we have here large derivations, right? 10%, minus 10%, etc. It's not yet the best thing in the world. We see here now another visualization. That's the green now is the stock price, and we see the hedge position here, right, which goes down accordingly over time. If this is now optimal or not, I won't comment on that, but this is what the action has chosen, the agent has chosen as action, step by step here, going through that. Of course, we can train the agent a little bit further, right? So I can get back here and can restart the whole exercise, and we would probably, hopefully, expect slightly better results in this context compared to what we have seen before. We would love to have a more flattened P&L curve, for example. And yeah, the best you see is a little bit higher than what we had before, but still lots of exploration going on, meaning that we in between will see still highly negative values like minus 84. Before it was minus 8. And yeah, so it goes through. Given that this is taking now a bit of time, so I see here another slight improvement with regard to the best result. I want to show you, and I have executed this Jupyter notebook up front because the learning here takes quite a bit. Beginning the same, now MLP regressor instead of Keras. And here, yeah, as before, nothing new. This as before. Of course, we now need to adjust this to the structure that we have. We have 5 data points in the state and 1 label value. Here, the optimal action works exactly the same. I think this should be exactly the same. I cannot spot any difference here. The major difference, of course, here is that we work with a completely different package, right? It could be a different model for the approximation, for the representation state in this context. Learning, same. Testing, also here based on optimal action for sure. These ideas simply remain the same. The finance environment is exactly the same, but I pointed this out that we have here, and again, I cannot explain it, not yet, maybe, hopefully soon, can I explain it, but this works better, much better here with the absolute differences, which is what I got started with in the first place. Then with the neural network before, the results were significantly improved when I changed to the percentage differences, but here it works better with the absolute differences. So and then we have, maybe give me 1 second, my dog is somehow sorry again, I'm alone today with the dogs. There were some emergencies going on. So with regard to the training here, I said it based on absolute rewards, it's working much better. And you see here the absolute reward, the best that we see now in dollar terms, right? Before, I mean, the numbers look like similar, but these are dollar terms now, right? Before we had percentage values. So we need to be careful what we are dealing with in this context. But for example, here, accumulated penalty of minus 0.257 doesn't look too bad. And when we do the testing down here, we see, values minus 0.54, minus 0.32, and these are accumulated values over the whole hatching. So here it shows now another test case, completely different constellation to what we had seen before, right? Now S is relatively high, here, right? Given the constellation, what do we have? We have K 0.9, sigma 10%, here ST 1.02, and the percentage values and the P&Ls. So here, compared to the case that we have seen before, just a couple of values, just 5 values here, I would say this looks a little bit better than what we have seen before, right? So when I change to the other one, where the values right here, we have percentage differences, -3%, plus 2.2%, 2.3%, and this has come down here in this context tremendously. So this can be now the case that by chance this particular run, right, episode 251, simply was an easy one, a better one, a lucky one, as compared to the other ones, or it can be that here this model works better, right? But we can have a look at this particular case graphically. Same graphic that we have seen before. Here the phi is the portfolio, the dashed green one is the value of the option, and red is the stock price. This looks here okay, but I think the next one is what we are interested in more. And the values here, so this P&L line, I guess, is quite a bit better than what we have seen before, right? Here we have now, of course, starting around 0, slightly going up, then slightly going down and up. So this looks here more dramatic than it is, I would say, because we go up here 2 cents and then 4 cents down compared to the other case that we have inspected before here, right? This goes down to minus 0.5, so minus 15 cents, right? That's quite a difference to what we see here. Again, I'm not implying here that this is overall and here they're much better, but these are simply 2 different cases based on 2 different representation networks, and that one for sure makes a better impression. So it looks like a dramatic fall, but it's not like the biggest thing in the world when we're dealing just with a few cents here differences. Also with regard to the percentage values, so highest derivation +4, -2 point something here compared to +10 and -10, and here the absolute derivations look also pretty good. You see here in the representation that there are, I would say, some breaks, some structural breaks, right? Because this jumping up and down here, this I would say it doesn't really make sense given how the value of the option is changing over time. So here I would say this is still room for improvement for sure. For example, based on additional training time, based on additional exposure of the agent to other data sets, right? In the other case, this was more smoother. We also have here some things that might look like a jump, but not like these like structural breaks that we see with the other model. So the other model can maybe even be further improved upon when we train it more. But having spoken of to train more, we now have done, it's finished after 3 minutes and it takes longer, right? Here we still have 60%, but this means 17 percentage points now more optimization instead of exploration. We now do the testing exclusively relying on exploitation and optimization. Every single run now takes quite a bit. Oh, that doesn't look too good. Minus 17%, we have seen better results, right? 0 is what we would like to have. Yeah, minus 12 is better than minus 17 for sure. And the final one. And when you wonder why I have here n minus equal 0, I just want to change. So I do 3 tests, and if you are interested in the other tests, right, you can go -1 or -2, so that you can expect the test case. Inspecting the training runs, I think doesn't really make sense given that we still have 60% exploration. So you would see random behavior throughout. But with the test runs, we have complete reliance on the neural network as it stands at this point in time. Yeah, another case here, the option loses value over time, right? Expires then worthless. In between here, a little bit better, but then worse again. The P&L, that's the interesting part. I think that's now better. It's still not a flat line, but again, we need to be careful with the scaling. So compared to our minus 15 cents that we lost, here it's plus 7 cents. And I'm not talking about that plus is better than minus. I'm talking about the absolute difference here, and I would say absolute term 7 is better than 15, and that's basically my argument. Let's see here, minus 10 plus 10. This was really wide still, and here it's actually worse. So this can we need to be careful also with the percentage values. So we need to have a look at both of them. So when you have an option that expires worthless and that it closes in on a value of 0, then even the slightest differences can have high percentage derivations, right? So the percentage values are more relevant and significant when you have an in the money option with positive value, but an out of the money option which has a pretty low or even value of 0, close to 0, and then the percentage values are not that meaningful. Then we have rather a look at the absolute values, and this doesn't look too bad here, right? Minus 1 cent plus 1 cent, that's not that much of a spread. With regard to the hedge position, there you see this is basically going down, and then sticks here to the 0 line. If this is optimal here in this context, given the evolution, I would really doubt in this context. But we have 2 more test cases that we have simulated. This is what I was saying. I can go here with -1 maybe, then we have another case. And yeah, this is now a case where we have obviously an in the money option, right? The price rises here to 1.4 and the strike price is 1, meaning it's absolutely in the money, right? The P&L, this context now getting negative, but we also see here another, how should I say, relationship. When we have high option values, then of course the chance for a high absolute P&L value, or here penalty, right, is higher, right? Therefore here you see it accumulates then more quickly over time, and we end up with -30 at the total P&L. Here now again, maybe more meaningful, the P&L in percent and P&L in dollar, also kind of okay. Let's see how the now we have the situation that we have encountered before with the other model that we have here. Obviously structural breaks, and here in the second part it doesn't seem to get it correct, for sure not, right? So this is then where later on the problems arise. So this doesn't look like a proper thing here in this context, right? So we would need to train this quite a bit more, right? Maybe one final look, we have one more, or maybe we have a look at another one here. So this was the structural break in the MLP regressor model. We have now seen a similar structural break in the TensorFlow model. So this was -2. We'll go with -1. But that's another case, right? Everything random. every single case is another one, right? And here the P&L is, again, the scaling is important. Highest value that we achieve is slightly above 5 cents. So this again looks a little bit more dramatic than it is, I would say, for practical purposes. And it ends up with a slight profit, but the absolute difference is not that large. Here, the P&L in percentage values, again, like -5, +7.5, but the absolute differences, they are pretty small here, right? So 0.00 5 upper and lower limit. That's not that large, I would say. Let's see. Yeah, the hedging now doesn't show the hedge position doesn't show the breaks that we have seen before, but still we have it here in the middle part, right? You see here where it jumps down, jumps up, jumps down. So it should be more continuous, like what we see here in this context, right? Yeah, that's the first control problem that we have encountered. Again, this is for me considered work in progress, but at least it works. If not perfect, it works. The agent can learn the trick, meaning to hedge an option, at least to the extent shown here. We can, of course, always do more training, maybe increase the capacity of the network, do, I don't know, 500 episodes instead of just 50 episodes, for example. Of course, all this is possible, but I wanted to focus here on the major differences to the discrete action case. And again, I would be happy if you have feedback in this regard. The code is available in the GitHub repository. I will push it up. I've done minor changes here. I will commit and push it to the repo right after this session so that I can play around with it. And again, I'm happy to get feedback and learn maybe how to improve certain things, because for me, this was the first time that I've done it and I haven't had any blueprint from somebody else doing this. Maybe I wasn't still unlucky with my search, and maybe you can point me to a resource or give me some feedback with regards to opportunities and potential for improvement that you see in this context. If there are no questions, I think there are no questions open. Quickly check. No, that's true. Then I think it's a good point to close today's session. Reinforcement learning in finance, now in quantitative finance. So not only from playing games to algorithmic trading, but now even a step further to the quant finance, mathematical finance, computational finance area of hedging, for the hedging of options. And what is kind of interesting, and you might have read this a couple of times, I don't know if I emphasize this regularly, but what we do here is basically a model-free learning, right? We do not have any idea embedded into the agent, let's say, of the Black-Scholes-Merton pricing model, right? We just have it indirectly, right? We derive prices and put it in as a state, but this is just to simulate what would be the case in the real world, because we can observe obviously option prices in the markets, at least of liquidly traded options, right? And therefore, I think it's better to put this into the state. But how this model, Black-Scholes-Merton model, comes up, given the assumptions with the price, is not known to the agent. So the agent basically learns what delta hedging is just by observing current stock price, time to maturity, the price of the call option itself, and then by getting feedback with regard to the hedge position that the agent in the beginning sets up randomly, and later on more and more based on the exploitation of the updated, trained, learned policy in this context. So I think pretty interesting approach, and more to be explored here, and more to come soon, I would guess. In that sense, I wish you happy reinforcement learning and hedging of options. I see you in the next webinar. Take care in the meantime. Bye-bye.